So eventually we will start studying the class equation for a group, which has to do with the conjugacy classes. But before that, I thought I would talk more broadly about what is conjugation anyways. So this is a bit more expository in nature, but I thought it was worthwhile because it gives a bit of the history behind the concept of conjugation in groups anyways. So we've already seen the definition. It's a specific group action of G on itself. Whereas we've seen, I usually write it as a power on the left, so it's a little easier to read it. But it's always a good question, where did this concept even come from? Because it seems to come from nowhere in the textbook. And the other fact, is that we've also talked about power sets. So, you could have G act on an entire set by conjugating every single element in the set. And it's like, where do we get such wonderful actions? Why would we think of these two things in the first place? I mean, we sort of seen this concept in some cases. It's explained as sort of saying, well, when G inverse is equal to A, that's saying that G and A commute. But conjugation is about more than just commutativity. So let's explore the origins of the concept. Let's go back to linear algebra. So, finite dimensional vector space over a field. Okay, let's just make our lives easier. We're working over Rn with its special basis E1 through En. We remember what a linear transformation is. It is any function that is additive, meaning that if you take, so that will A, BV, any linear combination of two vectors and apply the function, you're going to get a linear combination of the outputs of the function. That's true for any two vector spaces, but here I'm just going to talk about linear transformations from Rn to itself. And so one of the facts from linear algebra is that once you have a basis, L of u, or L of x I should say, can be written as A times x for some matrix. That's one of the things you usually learn in an undergraduate linear algebra course. Namely, you take the basis vectors and compute the output of the linear transformation, write it as a linear combination of the basis vectors, and that usually gives you the idea. So LEI is going to be some linear combination of basis vectors. I usually screw this calculation up, but I think it should be AJI. So some constants which depend on J and depend on I. These constants exist by linear algebra considerations, and so you group them together by matrix and you realize that in general for any arbitrary vector, it can be written as a linear combination of the basis vectors by linearity. You get that that's equal to the linear transformation, the sum of the values of the linear transformation, which apparently is equal to this matrix multiplication. By the way, it's worth pointing out this is already just A times EI by definition. And voila, the proof, if you needed the reminder, is that linear transformations when you have a fixed basis or equivalent to matrix multiplication. The other fact from linear algebra we often remember is that AE1 through AEN is a basis if and only if the matrix is invertible, or in other words, the determinant is non-zero. And that is our two facts so far. So, what I want to point out is the first place where you see conjugation in mathematics is in linear algebra. And there it occurs when you're talking about writing down change of basis. So you want to rewrite down a formula for your linear transformation in terms of a new basis. So what do? Well, you've already written that L is matrix multiplication, but you have a new basis. Which is given by multiplying each of your standard basis vectors by some invertible matrix B. Well, how do you rewrite L in terms of the new basis? Well, it turns out that L can be written down this way. And that's a fact from linear algebra. And this underlines a lot of linear algebra. They talk about similarity of matrices, which is an equivalence relation. Two matrices are similar if and only if A is equal to X or Px P inverse for some invertible matrix P. What's really going on from the modern algebra perspective is that you have a group action. So I'm not going to use A because we've been using A already for matrices. Let's use X. Let's let this be the set of linear transformation. Or we'll just say matrices. N by n matrices in R to the n. Then the general linear group, the invertible matrices, acts on this set via conjugation. And so the definition of similarity in linear algebra is nothing more than the orbit equivalence relation we discussed last time, just in this particular special case with this particular group action. So there's a bit of the origin of why we started discussing conjugating elements by other elements in a group. But that doesn't explain where we got the idea of conjugating subsets. Well, you already know from examples that we normally just conjugate subgroups, but where did that idea come from? So here's the setup. Suppose you have two permutation groups, G and H. One is in the symmetric group on A, the other is in the symmetric group on B. How on earth can you compare them? Well, similar to linear algebra, how do you compare vector spaces? Well, if you can make a linear isomorphism or a change of basis, you can make comparisons. So the point is, if there's a bijection between A and B, then we can talk about whether or not G and H are the same group. So suppose you've got a bijection, then it should be possible to ask whether or not G and H are isomorphic as permutation groups. Note that's different than as groups. Why? Because in this case, you're actually keeping track of the fact that they're permutations of a set. And so what would be the feature you'd want? Well, you would certainly want that for all pi in SA, sigma, so let's see, let's do this carefully. Basically, what's happening here is sigma is a bijection from A to B. You have a permutation on A. How do you get a permutation on B? Well, what do you have to do? You have to apply sigma inverse. That takes any element in B, gives you an element in A. Now permute it in A, and then send it back to B. This gives you a valid permutation in B. Oh, this should be G, by the way. So you see, you have this similar change of basis idea going on. This is sort of changing the labeling on A to B. So think of these as, if you're using 1, 2, 3 for your permutations, and I was using little a, little b, little c, then there would be an obvious bijection between the two sets I could use to rewrite the permutation 1, 2, 3 as the permutation that sends A to B to C. And that's what this idea is doing. It's actually writing down the formula you would need to carry out this construction in general. Now this isn't quite conjugation because sigma is a bijection between two different sets. But we do have this concept of isomorphism of permutation groups. It's no longer studied as well as it used to be, but it does exist. And so, of course, it does lead to the concept that you could talk about what happens when A is the same as B. In that case, now you're talking about bijections from A to itself. And so now you're talking about actual conjugation. And so what are you saying? You're saying that G and H, both subgroups of the same symmetric group, are isomorphic as permutation groups. If and only if we have this feature, that you've got a bijection that has this particular property. But you can check, what does this property mean? This property means that sigma G sigma inverse is equal to H. So you suddenly see our notion of conjugation of subsets that we've been talking about previously for group actions. So given a permutation from a set to itself, you now have the notion of isomorphic permutation groups. Two permutation groups of the same degree are isomorphic if and only if they're a conjugate. And so historically, this is where the notion of conjugation of subgroups originated from, and the slide on matrices is where the notion of conjugation in general originated from. The idea in both cases was sort of a change in basis concept. So here you're changing your labels, you're relabeling 1, 2, 3, and deciding that 1 is now 3, and so on.